Actually, hi everyone. Again, I would like to thank to me informing such kind words for me. Actually, and then again, thank you for thank you for coming my webinar. And then first of all, I would like to thank Dr. Seminerleri and the entire team for inviting me such an organization again. And then today I will present you such details about my work entitled Photodetector Array Technology based on individual graphene electrode and on silicon-oninsulator integration. I am a lithographer at Ermaksanot'ta Electronic R&D Center, and before starting actually my presentation, again I would like to inform about myself. My expertising area is examining the lithography process of semiconductor devices and then growth and fabrication of 2D materials and their structural, optoelectronic, and electronic characterizations. And about 3 months ago, I earned my PhD degree at the Photonic Science and Engineering Department at İzmir Institute of Technology. And this is my this is my actually outline, and my outline contains the motivation, introduction, experimental works, results and discussion, and then my talk will be over after giving my conclusion of my work. And to start with the sorry for that. To start with the motivation part, actually is the observing the pioneering methods for design, fabrication procedures, and performance evaluation of graphene and N-type silicon-based self-powered one-dimensional photodetector arrays on silicon-on-insulator substrate, working with hybrid absorption mechanism, because graphene and silicon has the different two absorption mechanisms, and due to the for example, due to the band gap of the silicon, and then low optical crosstalk is needed to get the high performance photodetector arrays, and broadband operation is also required, and high responsivity, fast recovery time, and also the most important thing is the ease of fabrication and the low cost. Today, I will give such the information about the single pixel photodetector, and then the final side, the final work will be the one-dimensional photodetector array with separate graphene electrode. To start with the introduction part, the silicon-based photodetector arrays actually including the one-dimensional and the two-dimensional photodetector arrays. The one-dimensional photodetector arrays is containing the multiple silicon photodetectors arranged in a single package. Here you can see the image of the linear array silicon PIN photodetector, and the two-dimensional photodetector arrays is the comprising an X and Y axis aligned mosaic-like device structure. Here you can see the 4x4 photodetector arrays, but these detector arrays have the drawbacks. They are to start with the drawbacks of that, then is the silicon dies. Actually, here you can see the dies, the smallest parts with the silicon detectors with should be arranged with a micron precision, and they are cut and then stack them in arrays, which requires the high-cost packaging methods. And also these silicon-based photodetector arrays operate in the bias condition. So we require to minimize the energy consumption is required the detector arrays which is working at the self-powered without any bias condition. And here you can see the usage area of the photodetector arrays. They are using in the in the laser scanner applications, detection of the light in spectral photometers, and optical fiber communications, image sensors, and the position and motion detection. So here you can see the two-dimensional photodetector arrays, the use area, and the one-dimensional one using in our daily life. To introduce the silicon-on-insulator technology, these wafers and this technology also provides the new functionality for the advanced silicon devices. Here you can see the fabrication of the silicon-on-insulator wafer. Here is the first one is the oxidizing the bulk silicon wafer, and then the bonding and annealing of the bonded silicon wafer onto the silicon oxide side, and then thinning of the device layer, which is the vested one, and then we get this sandwich structure. Here the bulk silicon is using as the supporting layer, and between the prime quality silicon layer is also the name as the device layer, and then the support substrate is the silicon oxide layer, which is also acts as a well-defined edge top layer, and the top of the wafer is the active layer, is containing the n-type silicon again, as working as a device or the active layer, and this silicon layer has the prime quality. This technology allows full dielectric isolation and reduced leakage currents and full depletion of the active silicon layer for high speed and the lower power applications. Actually, this full depletion layer is controlled by the active layer thickness. Here you can see these numbers. The thickness layers, the number of the thickness layer is required with our study, and this technology is can be used as the RF circuits, silicon photonics, silicon optoelectronics, microelectromechanical systems, power electronics, and etc. To continue with the graphene, as we know that the graphene is a single layer of carbon atoms forming honeycomb lattice. This graphene material is known as the semi-metal without band gap, and it has high transmittance when compared with the indium tenoxide material, and the graphene has high electrical conductivity. In graphene lattice, there are two different bonds, P bond and the sigma bond. Here P bond is here P bond is the weakest bond, namely van der Waals, and this bond is related pioneering the electronic properties of the graphene, and the sigma bond is the strong covalent one, and it is related with the pioneers the mechanical properties of the graphene, and then the graphene energy band distribution is required the linear one, and then this linearity gives the graphene has the highest optical and electronic properties. And here you can see the energy band diagram of the graphene. Here the different Fermi levels. Due to the doping type, graphene can be also named as the semiconducting materials due to the doping. Actually, to continue with the production methods, here in our study, we use the chemical vapor deposition method. This method is related to decomposing hydrocarbons on transition metal surface at high temperatures. By the way, graphene is synthesized by this way, and then this method, the transition metals, different transition metals can be used, but the well-known and the most feasible catalyst is the copper, due to the low carbon solubility, low cost, and it is very easy to graphene transfer to another desired substrate with this transition metal. This method has these advantages. Here, grown graphene has high quality, and the large scale production is also easy, and the growth and at atmospheric and low pressure is also possible with this method, and the reproducibility is very good. Okay, I mentioned the silicon-oninsulator technology and then graphene. What if we combine, for example, the silicon and the graphene in touch? So these slides will tell me about this one. So for actually to get the Schottky junction, for example, for N-type silicon or N-type another semiconductor, the work function of the metal should be greater than increased than the semiconductor one. Here you can see different. Here you can see the different two materials like the metal and the N-type semiconductor before contact. After contact, these two different materials, due to the charge transfer, the band bending occurring and the thermal levels are getting aligned due to the charge transfer. So, as I said that before, we choose the Schottky junction. This is related with actually the metal and N-type semiconductor. Generally, metal contact and the silicon contact, when combined to each other, Schottky junction is occurred. But we know that when the light strikes onto the junction, electron hole pairs are generating. By the way, due to the wavelength of due to the energy of the light. Here, generally, metal contacts are using less than 10 nanometer, and drawbacks of the metal contact is here that due to the high reflectivity, by the way, the low quantum efficiency, and the most important thing here is the thermal level of metal is not tunable. This is the highest drawback of this structure, and the transparency depends on the thickness of the metal. If you use thicker the metal contact here, by the way, your device performance will be very, very bad. So the depletion region is occurring when two different materials here combine each other, and the depletion region is related with the responsivity, detectivity, and etc. By the way, the performance of your devices due to the electron hole pair is occurring in the depletion region. What if we combine the graphene and N-type semiconductor like N-type silicon? Here you can see the studies the combination of the graphene and silicon heterojunction layer. Here, generally, N-type silicon used as a photon absorption layer that collects the electrons, and graphene is used as a transparent conductive electrode and collects holes. Even under the self-powered condition, when you strike the light to the junction, the electron hole pairs can be occurred easily due to the large electric field occurring in the depletion region. By the way, as I said before, self-powered photovoltaic mode is available for these devices, and the fabrication is very easy, and the broadband photodetection is possible. And the most important thing, the most important property when compared with the metal one. Graphene as a metal has the tunable thermal level, and then by the way, the Schottky barrier height. When continuing with the fabrication side, the photolithography is used to get the N-type silicon arrays. Here you can see the positive phone resist dropping the N-type silicon side, and then to get the active layer shape, we use reactive ion etching mechanism, and then we measured the thickness of the silicon side. Here you can see the 10 micrometer as the desired thickness of our silicon-insulator substrate, and then we deposit the metal contact on the device. So you can see the final device shape with a 1 millimeter to the 1 millimeter size. This is the thermal atmospheric pressure chemical vapor deposition setup located at the Quantum Device Laboratory, ISTEC. So we grow the graphene with a dimension of the 10 millimeter to the 10 millimeter on the copper foil. The chemical vapor deposition methods actually require the heating, annealing, growth, and cooling steps. Before growth, you can see the optical microscope image of the copper foil. There are such traces here. And then after growth, with the annealing, with the help of the annealing, the grain boundaries are getting enlarged. So by the way, the large area graphene without or the low defective side can be grown easily with these. Here you can see the monolayer graphene parameters. With these parameters, it's also possible defective, less defective graphene. Graphene transfer is required here 6 different steps. Here the copper foil and the grown graphene on the copper foil, and then after drop casting method, the drop casting of the photoresist onto the graphene side, we etch the copper foil by using ferric chloride solution. After dissolving the ferric chloride solution into the DI water by removing the residues, we baked the photoresist graphene onto the desired substrate at 100 Celsius degree during the 5 minutes, and then we remove the photoresist using the acetone. Here you can see the schematic illustration of the graphene transfer procedure used in this study. After getting the device, we had to characterize it. Actually, the surface characterization was done by using scanning electron microscopy, optical microscope, and also Raman spectroscopy. One of the fingerprint characterization method of the number of layers of the graphene and also the quality of the graphene is the Raman spectroscopy without any damaging of the layer. Here you can see 3 different peaks: D peak, G peak, and the 2D peak. These are related with the graphene peaks. The intensity of the 2D with respect to the G peak gives actually the number of layers. The intensity of the 2D peak with respect to the G peak is also actually the D peak and the 2D peak is the second order peak of the D peak. I'm talking about 2D peak here. The intensity ratio of the D peak to the with respect to the G peak gives the quality of the graphene. By the way, the homogeneity, as I said, the number of layers and the quality of the transfer graphene can be easily characterized by using Raman spectroscopy. And the homogeneity, defects, and residues, and also the coverage and the cracks over the device can be characterized and also characterizing using the scanning electron microscopy and optical microscope easily. When we continue with the current voltage and spectral response measurements of our devices, here you can see the optical and electronical measurement setup located at the our laboratory, quantum device laboratory. Here we use the current versus voltage characteristics of the devices in a dark environment at the room temperature to get the ideality factor, Schottky barrier height, and the sheet resistance of the devices, and the responsivity versus wavelength measurements were also done to get the characterize our arrays, detector arrays. Light power dependent current versus voltage measurements was done to compare the photoresponse characteristics of the single pixel graphene n-type silicon Schottky photodetector on silicon-on-insulator substrate with the reference detector. Here is the reference detector is the graphene n-type silicon Schottky junction fabricated onto the bulk silicon one. Here we use the LED source and laser line filter and the high power LED driver with pulse modulation to inform to get the information about the power dependent our devices. And we continued with the time result photocurrent measurements to determine the speed of the arrayed devices. Here you can see the common electrode one devices, but I will not. I will skip this study, but because my speech is only related with the detector arrays with the separated one. Here we used oscilloscope, function generator, power LED, and here you can see our device. Our device is related with, as I said before, the separated graphene electrode one. Here you can see the rise time and the decay time or the fall time. This actually rise time and the decay time is the range that the photocurrent rises from the 10 to the 90% of its maximum value. By the way, we can easily detect the rise and the fall time of our detector arrays by using this. The most important thing is actually for the detector arrays on a single substrate is the optical crosstalk measurements. This is done to determine that each graphene n-type silicon diodes work independently of each other. Here you can see the detectors light is striking on the junction. Here we kept the distance same to minimize the possible back reflections and the well-defined spot size using the fiber optical cable at a 1 millimeter distance, and then we did this experiment for each detector arrays and then collected data from them. Actually, as I said before, we have to compare the detector array, graphene and silicon detector array with the reference one. By the way, we fabricated the graphene and silicon-on-insulator device and the graphene and silicon device as a reference one with the same active area, and also the device layer, the electrical properties of the device layer is also kept constant to see the effect of the photoactive layer thickness, because we know that the only difference is the photoactive layer thickness. So we have to compare we have to compare these before starting the fabrication of the array structure. This is the fabrication steps. Here you can see the graphene and silicon Schottky junction and the graphene on silicon-oninsulator Schottky junction, single pixel detectors. Here the fabrication procedures is related with the graphene and related with the reference one, starting with the deposition of the silicon oxide layer by thermal evaporator, and then depositing the metal contacts onto the device, and then the transfer of the graphene. And the graphene and silicon-on-insulator single pixel device is related with the opening the window and the etching through the silicon oxide layer on the silicon-on-insulator structure, and then depositing the metal contacts onto the devices, then the graphene transfer. Here, as I said before, the active area was kept constant for both devices. When we look at the electrical characterization of these two different device structures, here you can see the dark current of both structures are very, very good, very low to get the work with the high performance photodetectors. It requires very low in the nanoampere scale, and the I-delta factor and the Schottky barrier height of devices were done with the and also these were done by actually the thermionic emission model equation, and then by using the Cheung's functions, we observed the sheet resistance and the I-delta factor of the devices. Here you can see that both devices have the rectification behavior. To continue with the photoresponse characteristics of both devices, here you can see the results with a 905 nanometer light under the different light powers. Here, at the left one, the photoresponse mechanism with the increasing the power level of, here you can see the linearity, for example, in the photocurrent, and the non-linearity one in the other device. But I have to focus on the mechanism here, the short circuit current of devices and the open circuit potential. Here, the open circuit potential is related with the Schottky barrier height, and the short circuit current is related to the power of the light. So, with increasing power, both devices give the photoresponse, but in the for the graphene and silicon-on-insulator substrate single pixel one, this is very low. So, and also we observed that there is a nonlinear behavior with an increasing power. So we have to understand this mechanism. So we have to check the responsivity. We have to check the responsivity of the devices with an through the visible scale and through the near infrared region, because we know that the actually this is related with the absorbing material. Here the band gap of the silicon is 1.11 electron volt. After this value, both devices will be over that actually. So when compared with these two devices, here you can see the blue dashed the bulk silicon, the device with the fabricated on the bulk silicon, and the red one is relating with the result of the responsivity result of the graphene and silicon-on-insulator substrate device. When we check that, both devices show different photoresponse mechanisms. So for bulk case, the maximum responsivity occurred at 905 nanometer. By the way, actually, with the previous experiment, we choose this light source, and then the graphene insulator substrate gave the lowest wavelength, the maximum responsivity at lowest wavelength. So you can see the second peak. This peak also related with the photon absorption, photon penetration depth. By the way, after these wavelength, both detectors are getting, actually for the 100 nanometer case will be that. For all experiments were done under the self-powered conditions, and then we get nearly the same photoresponse values because we use the same active area of the graphene in the junction. Here you can see the schematic of the incident and reflected light through the substrates. When we consider that for the bulk one, here you can see the incident light and the absorbing one, and then the reflected light. For the bulk side, there is only one mechanism. However, for the silicon-on-insulator case, incident light can be reflect and can be transmit over the substrate more than one times. By the way, these behavior related with the oscillation. Here you can see such an oscillatory behavior for the graphene and silicon-on-insulator device. As the wavelength of the light increases, we know that it penetrates deeper into the silicon substrate. For the silicon-on-insulator case, for the lowest wavelength of light can penetrate due to the active layer for the 780 nanometer. For the highest value of this light cannot be penetrate through the bulk silicon case because of the silicon dioxide layer, which is containing in the silicon-on-insulator substrate. We know that the photon penetration depth is also related with the inverse of the absorption coefficient of the material, and then there is no contribution to the photoresponse over these nanometer. By the way, this is the result of this getting lowest of the photoresponsivity value of the graphene and silicon-on-insulator substrate. And also we have to consider the light trapping concepts in thick and bulk silicon case. As I said in the previous slide, the lowest wavelength penetrates through the active silicon layer. However, for the highest wavelengths cannot be penetrate to the deeper side. And also it is related with the depletion region of this junction. So here, when we consider the built-in potential value and the doping concentration of the active silicon layer in silicon-on-insulator substrate, we calculated the depletion region as a nearly 1 micrometer. By the way, the 1 micrometer is related with the photoresponsivity thickness, because electron hole pairs are occurring in the depletion region. We actually concluded for this responsivity value in shorter wavelengths, actually we know that only drift currents can contribute to the photoresponse mechanism. However, in the longer wavelengths, both drift and diffusion currents can contribute to the maximum responsivity of the devices. The second one, as I said, that the linear array structures, linear arrays, N-type silicon structures on silicon-on-insulator substrate with common graphene electrode. Actually, as I said, that I will not give any detail for this work, but we checked first this is possible or not, and actually published at Applied Physics Letters as an editorial peak. And after that, we fabricated the individual electrodes, individual graphene electrodes on silicon-on-insulator substrate. These fabrication routes actually including 3 different steps. First one is getting the N-type silicon array patterning, and then second one is the graphene patterning after transferring on the substrate, and then third one is the metal contact deposition and liftoff. Again, you can see both two fabrication rules requiring the lithography steps, photolithography steps. By the way, we get these structures by using these fabrication methods. After getting the device structure, here you can see the active area of the individual diodes as an 3 mm square. When compared with the single pixel, actually this value is very, very low, and nearly 6 times lowest active area. And we get the linearity of the, we get the homogeneity of the, or the success of the device fabrication we check by using the optical microscope. We characterize it by using optical microscope, and then we get the homogeneity and the number of layers of the graphene by using Raman spectroscopy. Here we can see the defect peak is very low, and the intensity ratio of 2D and G peak related with the monolayer graphene can be transferred successfully on the device structure. And then we get the electronic measurement, we get the IV measurement of the devices under dark environment. We get the identity factors, and then the Schottky barrier height of these individual devices nearly the same, and then they are in a good agreement with them, with each other. And also the strong rectification here you can see is also observed after these experiments. The most important thing actually here, the measurement of the optical crosstalk between diodes. Here you can see different diodes, and namely D1, D2, D3, and D4. Here we use the same wavelength, the highest responsivity, same wavelength that we get the highest responsivity of the devices with this value. And then we use the same power density of the device of the light. Here we put the light, for example, the D2, we get the electron hole pair, and we get the photocurrent. However, we checked actually the other diodes can communicate each other or not. It should actually they don't work while striking the light onto the D2 one. So we get the results using this actually. Here you can see the light on silicon dioxide case and the light on the silicon. By the way, the active junction Here you can see both detectors gave the nearly the same photocurrent results, and with the same open circuit potential value and nearly the same values. And then here you can see the light to get the result on the silicon dioxide case, nearly the 5 nanoampere. This current value is the value that we get under the 0 volt value. These actually the dark current of the devices, nearly the 0.3 nanoampere. There are actually 10 times higher values. This is related with the backscattered, randomly backscattered light due to the metallic fiber, and then the silicon substrate, and then these increment is related with the with this mechanism. However, to get the total crosstalk result, we observed nearly 0.1% crosstalk is obtained for both detectors. We concluded that optical crosstalk between each pixels, each diode arrays, even the effects of the reflected light on the measured current, can be ignored, by the way. So this is very, very important result to get our experiments. After getting the optical crosstalk measurement, we have to consider the spectral responsivity, detectivity, and the noise equivalent power values of the devices. These values are related with the performance of the detectors. Here you can see nearly the same responsivity value, same detectivity value, and the actually calculated noise equivalent power very, very lowest and the same. By the way, by saying the same, all 4 detectors on the silicon-insulator substrate on a single substrate work independently each other, and they have the same value. All diodes, as I said, show the similar maximum responsivity. Oscillatory behavior in the spectral responsivity is also observed with this experiment due to the sandwich structure of the silicon-insulator, and the high sensitivity under the self-powered mode is achieved, and actually these small variations can be related with the quality or the doping concentration of the graphene in the measurement. The time result photocurrent measurement also done for each diodes. Here you can see the rise and the fall time or the decay time of these individual diodes is nearly 1.3 microsecond and 1.3 microsecond, which is respectively under the self-powered condition. For each diodes show the excellent photocurrent on-off reversibility, and then this is also the important result of the study. When I summarized and compare the common graphene electrode and the separate individual graphene electrode one, we observed the suppression of the nearly 150% optical crosstalk actually between the diodes, and when compared with the literature, actually the different fabrication routes or the designs, etc., can be applied, but the published one has the for the silicon case nearly 10% and the indium gallium arsenide based photodetector array is nearly 1%. Even when we consider these results, our detectors, even if the self-powered condition, show the excellent performance and also the lowest optical crosstalk value. These lowest optical crosstalk value is related with actually the graphene and silicon-on-insulator integration due to the absorption layer thickness. And then the device fabrication rules, because you can change the array, the geometry array, by the way, the photodiode size, pixel pitch, etc. By the way, we can suppress the optical crosstalk between the electrodes. When compared with the photoresponse properties with the literature, actually, here you can see different studies related to the graphene and silicon-on-insulator case. Actually, under the biased condition, our self-powered devices, even if the lowest active area compared with this literature, we get the actually excellent performance operate, and also our devices operated independently of each other with low dark current, low noise, by the way, high responsivity, relatively high responsivity, and high sensitivity under zero bias condition. Actually, to sum up, the photoresponse in first section, by fabricating the single pixel photodiode, we observed the photoresponse mechanisms of the devices on silicon-on-insulator substrate and compared with the reference one to get the effect of the photoactive layer. And then we observed the highest detection limit as well as the reference one under zero bias condition. In second section, we fabricated the photodiode array with common graphene electrode to achieve the second device structure, the individual one. We observed the multiple photodetector arrays can be produced simply by employing the single layer graphene as a common electrode, and then we skip the individual case, and then we observed the individual graphene electrodes suppressed the magnitude of the optical crosstalk by a factor of 150%, and all diodes in the array exhibited stroke rectification behavior with an fast operation speed. Actually, this is the proof of concept study, and it could be improved further to be used in our daily life with integration of graphene and silicon-on-insulator technology. Actually, this work, as Sanoja said at the beginning of the presentation, was supported by Yaşar University with a scientific research projects. And then I would like to thank for your attendance, and you can also scan the QRs to get the more information about the ion photonics by Ermaksan, my work, and then also you can scan these QRs, actually, as I said before, to get the more information about our laboratory, quantum device laboratory. And if you have such questions or etc., or any sharing about me, details, you can feel free to send me email. And then again, I would like to thank for your attendance.
Thank you very much, Alper. That was a nice presentation. Zeynep?
Yes, hocam.
Hello. Yes. Go on, please.
We would like to express our sincere gratitude and appreciation to Dr. Alper Yanılmaz for his informative presentation regarding his and his team's final study.